This video is about internal energy. No, not that kind of internal energy. I mean, internal energy is a term that we use in physics. So now that we're back in physics mode, let's first mention what internal energy is not. So internal energy is not the same thing as heat, even though many people get them mixed up. Heat is energy in transit. So basically when we have a hot object and a cold object, then heat is the energy moving from the hot one to the cold one because of their difference in temperature. So that's what heat is. Internal energy is related to heat, but it's not the same thing as heat. So the reason why it's related to heat is that when heat flows into a substance, its internal energy increases. So when we had the heat moving from hot to cold in this example, that means that the cold object is going to have more internal energy after the heat has flowed from hot to cold. And the hot object will have lost some internal energy because heat flowed out of the hot object. Maybe you're finding this a little difficult to picture, so let's use a simulation to help us imagine how this looks. Here we have a glass of water at room temperature, and we're going to see what happens to its internal energy when we cool it down or heat it up. So you can see the thermometer is at this level here, and also we can see all the internal energy being represented by this little E's. So first of all, if we're going to cool down this water, we see that the internal energy is leaving the water until now we reach the freezing point of water. So the temperature has now gone down to here, and if we heat up the water, then we see that we're adding internal energy to the water. So when heat flows into the substance, the internal energy increases. And you can see that when the water temperature is quite high, we're now losing quite a lot of energy into the air. And that's because water is now hotter than the air, so heat's going to flow from the water into the air. And if we replace the water with, for example, a block of iron. So this iron is again at room temperature. Let's get a thermometer. And it has a certain amount of internal energy. So the same thing with iron. If we're heating it up, we're adding internal energy. And when the iron gets hot, it's also losing heat to its surroundings. And we can also go backwards and cool it down and remove as much internal energy as we can. Right now we can't get any colder. But that's only in this simulation, because in real life we could keep removing internal energy until we reach absolute zero. It's only that this simulation only goes down to 0 degrees Celsius. So far we've seen how internal energy works on the macroscopic scale. But internal energy is actually defined in terms of the microscopic scale. So let's look at the molecular scale instead. Internal energy is related to the total energy of the molecules that make up a substance, and it consists of two components. One is the potential energy that the molecules have because of their intermolecular forces, and the other one is the kinetic energy that they have because they're moving. Now pay attention to the fact that we use total in this equation. So that means that we're not talking about the average potential and kinetic energies, we're talking about the total. So this is different from our definition of temperature, which was the average kinetic energy of the molecules. Because it's total here, that means that if we take twice as much of the same material, we actually have twice as much internal energy. That's if they have the same temperature, of course. Because if the temperature is higher, then the average kinetic energy is higher. And that means that the total kinetic energy would also be higher, so the internal energy is more overall. Let's write down our definition of internal energy again, but a bit abbreviated so we can see it a bit more. So internal energy is equal to potential energy plus kinetic energy. And let's talk a bit about each of these two in turn. So first of all, the potential energy is due to the forces between the molecules. So you can think of two molecules as having a spring between them. And that means that if we want to separate the two molecules, pull them further apart, then we have to do work against the force of the spring. And because we're doing work to separate them, that means that the two molecules that we're pulling apart are gaining potential energy. There's one exception to this, which is in a gas, because in a gas the molecules are so far apart that we can consider them to have zero potential energy. Now the kinetic energy of the molecules comes from three different parts. So the first one is the translational kinetic energy, which is the one we normally think about, because that's the one that's caused by the molecules simply moving around in straight lines. And there's also the rotational kinetic energy, which is just what it says, it's the molecule rotating. And finally there's vibrations of atoms within molecules. So within each molecule, say we have a molecule made of two atoms, we can see these two atoms as having a spring between them, just like we did with the molecules. Earlier we said that the molecules have springs between them to represent the forces between the molecules. We can do the same but on a smaller scale inside a molecule. So we've got these two atoms with a spring in between them, and they actually vibrate all the time, and that's also a source of kinetic energy. So we could say that the internal energy is the sum of four different types of energy. So we've got the potential energy, and then we have three types of kinetic energy. But that's only true for molecules that consist of at least two atoms, because there are also monatomic gases, like the noble gases, neon, argon, and so on. And in a monatomic gas, we're not going to have any vibrations of atoms within molecules, obviously, because there's only one atom. So the vibrational kinetic energy goes away. And it turns out that even the rotational kinetic energy we can neglect, because it has such a small effect. So even if atoms can be rotating, the energy effect of this is so small that we just ignore it. Now, I already said that gases have no potential energy. So if you think about it, if we take a monatomic gas, then that means that it's not going to have any potential energy, and it's also not going to have any vibrational or rotational kinetic energy. So all of its internal energy is translational kinetic energy. So that makes this system much easier to model, which is why we look a lot at ideal gases later on in this topic.